So hi everyone, I'm André Ferreira and I'm going to be presenting to you my paper on predictive medicine using interpretable recurrent neural networks. So for this paper we use this dataset of ALS patients from Lisbon, Portugal, in which we want to predict the non-invasive ventilation over the next 90 days. We have 840 patients and 46 features which range from demographics up to neurophysiological tests. So with this data, how can we facilitate AI in healthcare? Well, I really like this image of Christoph Molnar, which shows the main steps towards a successful ML project. And since you already have the data, we just want to focus on the three core pillars, which I like to call the performance, the interpretability, and the usability. But first, let's start with a bit of context. So, since I'm using multivariate time series data, recurrent neural networks are a good model for this kind of problem, as they are good at handling sequential data. So, just as a recap, they work like this for each timestamp t. They can update the memory ht with the current input x, they can calculate an output y, and then send the memory ht to the next identical cell through these equations that you see here. There's also these long short-term memory models, which reduce some of the risks of gradient problems by adding a new hidden memory cell C, which does pointwise operations instead of vector multiplications. Then there's this concept of time awareness in these models, which are just missing from these traditional recurrent models, which is the elapsed time between the samples, which can vary between the patients. And in this paper, we consider four possible solutions to this. We can just simply add the elapsed time as a feature, or use one of these three models which incorporate the elapsed time inside the cell itself, usually through modifications to the forget gates. Then there's the problem of interpretability. In this case, I focused on this SHAP technique, in which we have this concept. We have this interpreter model G, we have M possible features, we have this representation of feature presence for each feature, and we have the average output and the SHAP values of the features themselves. In this case, it represents how the feature contributes to the output. So how this works is that a local interpreter model is always trained for each sample, which iteratively hides some features by replacing them with background values. In this case, it attempts to match the original model's output with these modifications of the input. Then, for the performance part, as I have a lot of concepts that I want to test here, I built this modular framework in which we can combine multiple concepts. So let's go one by one. We can use one of 5 possible recurrent cells. We can make the models be bidirectional. We can also include an embedding layer or use the elapsed time as a feature. You have to have the time awareness. So with this, I tested all possible combinations of the models, and I also tested each one 3 different times with 3 different random seeds. So the main results here are these, that the bidirectional LSTM models really lead the performance ranking. We also see this kind of surprise that XGBoosts got comparable results, at least comparable to unidirectional models. And we also see this unfortunate result that intrinsically time-aware models have the worst performance. Perhaps the dataset here is so small that it doesn't justify the added parameters. In terms of interpretability, we see that kernel SHAP, its lack of assumptions on the model that allow it to be model agnostic, it stops it from working with these RNN-based models. What happens is that when we apply SHAP to these recurrent models, the sum of SHAP values does not always match the model's output, which was what we want to have. So to fix this, I dove deep into the kernel SHAP code and do some of these following changes. I added parameters that allow us to know when it is an RNN model, and then made it go sequence by sequence instead of sample by sample in the explanations. And I also then do the main change, which is the preserving the model's memory in each sequence, which was the main step to fix. Applying this custom SHAP package, we get this overall feature importance for this LSTM model and this XGBoost model. We see a similar distribution of most important features, in the sense that the 2 feature plots show similar distributions with 1 or 2 dominant features that both contain 3R, a respiratory symptom. We also see that the rest of the features in the top are usually present in both plots, even if they have a slightly different order. And this would be even more evident if we were to see a bigger list of features. And of course, having the dataset in context, we see that respiratory and mobility symptoms have the highest influence in the prediction of non-invasive ventilation, as it was expected to be. But well, in a multivariate time series context, feature importance might not be enough. Because while we have features, these features are inside samples, which are inside sequences. So we should also try to interpret how each sample affects the output. In this case, I developed 2 different scores. In this case, the initial approach is rather simple, just try to cover up one of the samples and see how that affects the final output. But this might not be enough because It may happen that a certain important event happens that has repercussions on the rest of the sequence, such as an aggravated symptom, for instance. In this case, I did this output variation score. But well, both can be relevant. So what I did here was to combine both in a weighted sum and did some modifications just to allow us to have a better highlighting of the most important scores. Then in terms of usability, in my opinion, regarding AI in healthcare, it can be addressed in two ways, by releasing coding packages and dashboards or no-code interfaces. In terms of packages, I made data utils, which contains most of the code that I did for this paper, and then also the model interpreter, which is more focused on the interpretability side of things. Then, so just to highlight a bit of this dashboard that I made, we have this homepage in which we can select the dataset and the model that we want to test. And it shows an overall report on how the model is like in this dataset and its interpretation. In this case, we can really see all the sequences of the patients, and the colors here are made with the instance importance plot that we saw before. In the case that the red colors indicate a high contribution to increasing the output score, and the blue ones are the opposite. In this case, we can highlight one or two different samples here and see how they are interpreted by our interpretability techniques. In this case, we see here the salient features over all the patient's sequence, the feature importance on the current sample, the final outcome of the patient, and the final output of the model. We can go a step further and edit this sample to see how some manual changes would impact this scenario. So, what we see here through the core pillars. We saw that LSTM-based models surpassed the baseline, and the main cause for this was bidirectionality, by far. Then we also, in terms of interpretability, adapted SHAP to RNN-type models and introduced a new instance importance score. We also released 2 packages to facilitate coding and implementation of these techniques, and also created a dashboard as a proof of concept. And that's it. I hope that you enjoyed this presentation.